Hi. Today we're finally going to start the last part of our course, which is integral calculus. So basically, this is the part of calculus concerning accumulation of quantities and areas below curves. And look, when we are going to start now integral calculus, we will have a little bit different, even if not to say opposite, task to do in comparison to what we had before when we were discussing differential calculus. Because look, let's just say, because we need to introduce some new notation, but just a little, that we have some primitive function. So let's denote this by capital letter F of x. And when we were learning about differential calculus, what we were doing is that we were calculating derivative dx out of the primitive function. So we were doing something called differentiation. And as a result, we were obtaining f of x, right? So our derivative function. Okay, now we're gonna move in the opposite direction. Look, now we are assuming that we have some derivative functions. So, lowercase f of x. And now, we're going to go through a process that is called integration. Which we will denote what it means, I will explain in a second. And, as a result, we are going to obtain primitive function. And this is what we're going to learn actually how to do today. But before we move on, let me just bring your attention to one thing. Look, here we have a symbol of differentiation. And look, I told you that we can think of a derivative as a ratio of two differentials, right? And this is what we have here, df of x over dx. And look, here, when we were in the process of finding derivative functions, so in the process of differentiation, we were dividing by dx. Here, when we are reversing this process, so when we are getting from derivative function to primitive function, what we get here is that also we use dx, but now we are multiplying by this dx. And look, as everything in mathematics, this is not a coincidence. But here we're going to approach integrals a little bit different than we did before. Because look, when we started derivatives, we actually started by explicitly illustrating what is derivative and what we are using it for. Then we've introduced rules that allowed us to calculate derivatives relatively easy. Today, what we're going to do is actually the opposite. Well, I'm going to start by showing you some rules that we can basically figure out once we know the rules of differentiation, and then we're going to move to explaining what those integrals truly are. Okay, but let's now get to this symbol. Okay, so let me just take some colors and this what you see over here is the expression we're going to use when we are going to perform integration. Now, this is called integral sign. This part, this function over here, so our derivative function is called integrand. And look, what we're going to obtain out of this is a function f of x. But look, once we are getting to this point, right away, something should be mentioned. Okay, let's say that you've got a function d, you've got derivative dy dx that is equal to 6x. Now my question is, what function has given us this derivative? Well, look, because we know how to perform differentiation, we can easily guess that. Look, because, well, definitely we're going to have x. And look, when we differentiate, we take from the power -1. So here we've got 1, here needs to be 2. Then we take this 2 and multiply up front, so we needed to have 3 over here, right? Because derivative of this clearly is 6x. And at some point, you might say, this is enough. What? Wouldn't we get exactly the same derivative if instead of 0 here, I would have +1? Well, we would, right? Because constant is gone in differentiation. If we would have a number like negative square root out of 1/7, still the same thing. If we would have here minus pi squared, exactly the same story. So look, the thing is that because in the process of differentiation we are losing a constant, we need to acknowledge this in the process of integration. What do I mean by that? Look, actually, there is not only one function that can give you this derivative, 6x. There is actually a family of different functions that will give us derivative 6x. If I would like to write that down, I could just put here plus c. Because look, as long as here we have expression without x, it's going to be gone in differentiation, and as a result, what we're going to have is derivative 6x. And this is the final ingredient that we need to introduce over here. Because every time when we differentiate, we are obtaining a family of functions that give a given derivative. So we need to finish with plus c, and the c we call constant of integration. Okay, so now we know all the basics. Because now we know all the basics of what we're supposed to do. So now let's move to the rules of differentiation. Okay, so let's start with something very easy, constant rule. And actually, we're gonna here do 2 of these rules. Look, first, what if I'm integrating 0? Well, if I'm integrating 0, then I should think about what is going to give me a derivative equal to 0. So what expression I need to differentiate to get 0? And the answer is very simple. It is a constant, right? Any constant differentiated is equal to, the differentiated constant is equal to 0. So over here, we will have just c. And remember, this is arbitrary constant. It can be any number. We cannot, without any additional information, we cannot specify. Okay, now, having this done, we might think about another case of a constant. Well, this is actually the special case of the rule we're going to do next, okay, a power rule, but let me just explain this first. So, look, now we are integrating k. So, how much should we get? Again, the thing is, what is the expression that will give us derivative k? And look, again, this is very easy, because if we get a constant derivative, it means we are dealing with linear function, right? So, if here we would have k x, right? Derivative would be simply k. So our answer over here should be kx, but we should also remember we will get derivative k if we will have plus c over here. So over here, of course, we will have plus c. So look, now if we have to integrate any number like 17, we will get that this is simply 17x plus c. Okay, look, from this moment on, I will be interested only in the expressions with x. We need to just remember that this that the constant of integration needs to be added in every case. Okay, so let's start with the power rule. Okay, let's start by remembering what did the power rule for differentiation look like. We had that derivative of x to the power of n is equal to n times x to the power n minus 1. Okay, so look, this actually allows us to figure out what should we do in the case where I want to actually do the opposite. So I want to know what is the integral of x to the power of n dx. Okay, so look, first thing we are noticing here is that here we used to have n, but then after differentiation we had n minus 1. So, look, probably if I want to integrate some function, instead of subtracting n, 1, I should be adding 1, right? That makes sense. But look, there's another problem. Here, n used to be over here, but now it's going up front. So, how should we deal with this? Look, in this, if this n goes up front, it means that we multiply by n. So now, if I want to reverse this process, I should probably divide by n. But again, we should not be concerned with n, but rather n plus 1. Okay, so I would say that this is a pretty good candidate for expression for integral. But let's check it. That's quite easy actually. All we've got to do is to differentiate this. If we're gonna get x to the power of n, it means that it works. Okay, so first thing I'm gonna do here is to put n plus 1 up front. And then I need to subtract 1 over here. And look, those two cancel each other to 1. Those two cancel each other to 0. We get n x to the power of n. So our solution works. So we can now easily write that integral of x to the power of n is equal to x to the power of n plus 1 divided by n plus 1 plus c. But now, when you look at this solution, you might say, wait. It cannot be that we can now use n in every power. Why? Well, definitely we see here n plus 1. And n plus 1 must be different than 0, which means that n must be different than -1. So remember, we can use this rule anytime we want, and when we have power function, unless n is equal to -1. And once we get to the logarithmic rule, it will become self-explanatory why we need to have it like this. Okay, so look, now let's do a couple of examples on integration so we get a better hang of it. Okay, so first, if I have integral, okay, first, let's consider the case of k, which we already discussed. Look, integral of k is the same as integral of k times x to the power of 0, which is 1, dx. Does it fall into this category? Yes, because 0 is different than -1. Okay, so look, by our rule, okay, I haven't introduced you one rule before that we can actually get this k out, but we will get to it a little bit later. Just trust me for now that we can. I'm gonna actually prove it, but that doesn't really matter. Okay, so look, how would it work over here? We would have k times x to the power 0 plus 1 divided by 0 plus 1 plus c, which would give us k times x to the power of 1 divided by 1 plus c. So, as you see, exactly the same result. Okay, what about if I have now integral of x dx? Again, this is going to be x to the power n plus 1, so 1 plus 1, which is 2, divided by the same number, 2 plus c. Okay, then we go further. We've got x to the power x cubed dx. So this is x to the power of 3 divided, x to the power of 4 divided by 4 plus c. But of course the rule works also with any numbers except for -1. So if I have, for example, expression like integral of 1 over square root of x to the power of 3 dx, I'm still able to deal with this case using the same rule, right? First, I can rewrite this as x to the power -3 over 2 dx. And what am I getting out of it? Look, first, I need to have x, and to the power of x, I need to add 1. So I'm going to have to the power negative 1 over 2. And this divided by negative 1 over 2 plus c. So look, if I'm dividing by negative 1 over 2, I'm getting negative 2 up front. Negative 2x to the power negative 1 over 2 plus c. Okay, let's try a couple more. I hope you're already getting a hang of it. But why not? Okay, so. So, what if we now have, for example, 1/5 root of x dx? Okay, again, we need to change this into the power expression. So we got x to the power 1 over 5, I'm sorry, dx. And we get that this is x to the power 6 over 5. X to the power 6 over 5. Remember, we are adding 1. Divided by 6 over 5 plus c. And look, this is a trick you also need to remember. If we divide by 6 over 5, it's the same as multiplying by 5 over 6. Now, x to the power 6 over 5 plus c. Okay, let's just do one more. So, if we have a cubic root out of x squared, what are we getting now? Again, dx. We need to first change it into exponential expression. We got x to the power 2 over 3 dx, and now we're adding 1 to the power, so we're getting 5 over 3 divided by 5 over 3 plus c. But dividing by 5 over 3 is like multiplying by 3 over 5. Then we've got x to the power 5 over 3 plus c. Okay. So, now that we've got the power rule down, we can move to the next rule. The next rule is the exponential rule, but of course here we will have a couple of them. So let's call them exponential rules. Okay, so let's start with the easiest case and remind ourselves what is the derivative of e to the power of x. This, of course, is e to the power of x. And knowing this, even without any further discussion, we can right away write that integral of e to the power of x dx must be equal to e to the power of x, of course, plus some c. Right? This is very easy. If derivative of the function is equal to the function itself, then of course integral must be as well. But of course we need to take into consideration that we need to add c at the very end. Okay, so now that we've dealt with this, how about a different case? What if now I want to differentiate function b to the power of x? We remember that this derivative gives us ln b times b to the power of x. Okay, so look, knowing this, we can try to actually figure out what is going to be integral of b to the power of x. Okay, because let's think about it. If derivative of b to the power of x is ln b times b to the power of x, then what would I need to have over here to get in total, let's do it like this, b to the power of x. Okay, and look, here, the new thing that appears during differentiation is ln(b). And this is what we want to get rid of. So if here I'm multiplying by ln(b), how about here I divide by ln(b)? Okay, so now if I'm differentiating this expression, I'm getting that this is ln(b) times b to the power of x divided by ln(b). Right? Remember, ln(b) is a constant. We don't need to use the quotient. Those two cancel each other out. We get b to the power of x. So, what we get out of this is that the integral of b to the power of x is the same as equal to, b to the power of x over ln(b) and of course plus c. And look, those are the two exponential rules that we've got. Well, the first is trivial, but as you see, using the second one is also pretty much very, very easy. But let's do an example. If I need to integrate 7 to the power of x dx, I'm going to get that this is going to be 7 to the power of x over ln 7 plus c. Okay, and I think this is it about exponential rule. The next thing, of course, we need to do now is the logarithmic rule. And of course, we're going to also have two, so let's call it logarithmic rules. Okay, again, let's start with differentiating natural logarithm of x. And look, when we were differentiating natural logarithm of x, we got that this is 1 over x. But 1 over x is the same as x to the power negative 1. So probably here, well, most definitely, we see that this is a case of the power function with n equal to negative 1. And look, that was the one missing case we had under the power rule. We couldn't find integral there, and the rule didn't work simply because function 1 over x is associated with the natural logarithm of x. Okay, and look, out of this, we should get right away the solution. So, if I'm going to calculate integral out of 1 over x, which is of course equal to x to the power negative 1 dx, which we also remember can write as integral dx over x, which is a relative change in x. But generally, I just want you to know that we can simply write it differently. Those two mean the same thing. Okay, then we should get here result that this is natural logarithm of x plus some c. But unfortunately, things here are not as easy as we would like them to be. Okay, and let me illustrate this on the graph. Look, before our task, okay, I'm going to try to draw them one over here and one over here. I'm going to try to draw here two functions. okay, so look, our first task was to find derivative of a function y equals ln x, right? We know that this point is 1. So, okay. And we were able to find the solution. We found that this is 1 over x. So here we have 1 and 1, x, y. And this function is y equals 1 over x. Okay, and look, so look how amazing is the result that we get. Let's just enjoy it for a second. Look, it turns out that if I want to know what is the slope of ln x at any point in its domain, all I need to do is to read this point from the hyperbolic function, so reciprocal function 1 over x. Well, this result is actually really convincing in a way that, look, I can clearly see here that the function ln x here is very strongly upward sloping, and here the values of the derivative are the height. Then the function gets flatter, and the value of the derivative gets closer and closer to 0, right? We can clearly see the correspondence between those two functions. But look, there is a trick over here. And what is this trick? Well, the trick is that when I write ln x, I instantly assume that x is bigger than 0, right? So when we were actually discussing derivative of x, we were discussing only positive values of x in the domain. But look, now we are going in opposite direction. We are starting with the function 1 over x. So this function is defined for both positive and negative values, right? It has a second part that, well, they should be perfectly symmetrical, but you need to forgive me. Okay, so look, what we know for sure is that if x is bigger than 0, then integral of 1 over x is this. Y equals ln x. Now, we need to have something that will work also over here. And look, we know that this function here is depicting derivative of the natural logarithm. So how this function should look like? We know that it should be downward sloping because all the values of the derivative here are negative. Then we see that at the beginning it should be declining, but at the very flat slope, and then it should get steeper and steeper and steeper and steeper and steeper and steeper as we get closer to 0. What shape would give us this information? Well, definitely. So let's figure out. We need to have downward sloping function. So this function will look like this. Then we see that at the beginning this function should be downward sloping, but at a relatively low pace, and then it gets steeper and steeper and getting lower and lower and lower. What did we get over here? Look, what we got over here is basically, if this is ln x, then what we see over here is a mirror reflection of ln x with respect to y-axis. what do we need to do with ln x in order to achieve this result? If you remember our first videos, in order to get mirror reflection over here, we can do this. I can put minus in front of x. But this wouldn't be good enough, right? Because then we would lose this part. The domain of the function would become real negative numbers, which is not what we want. Look, we want to have a function that is given for both positive and negative values, but not for 0. So there is a second possibility, and this is the possibility we're going to use. How about simply imposing absolute value on x? Look, now logarithm is defined for both sides, and because of this mirror property, it can serve, we can see that actually 1 over x is showing us the slope of this function. Okay, so the final thing we need to change in our result is that this formula works as long as x, let's write it for x bigger than 0. Which usually is enough for us, because in all economic applications, we rarely use variables that contain negative values. And of course here, we can write the more general formula that that integral of 1 over x dx is equal to natural logarithm of absolute value of x plus c for x different than 0. So we just need to remember to impose absolute value on x in our calculations. Okay, and again, I can easily generalize this rule to the case of logarithm with any base b, of course permitted, so positive and different from 1. So let's remind ourselves, what was the derivative of logarithm with base b out of x? That was 1 over ln b times x. So look, now what we are looking for is what function gives us derivative 1 over x and is somehow will be associated with logarithm b out of x. Okay, and look, we can clearly see that before we had a case with exponential function we multiplied by ln b. So the key was to divide by ln b, and this is exactly the same thing as we can do over here. Look, if I have ln b times logarithm b out of x, what will I get? The derivative of this is going to be ln b times 1 over ln b times x. Those two cancel each other out, we get 1 over x. Okay, so look, what we get in this situation is that the function we got, the situation we got can be generalized. So if I have 1 over x dx, this is equal to absolute value, well, it's equal to ln b times logarithm b out of x, absolute value of x plus c. But as you might notice right away, this rule is not very useful, right? Plus, we didn't have to go through all these steps to get it. Because look, based on logarithmic rule, that logarithm with base a out of b times logarithm with base b out of c is equal to logarithm with base a out of c. And look, what would we get out of this if I would use this rule? That would be simply ln absolute value of x plus c. So, even though we can make generalization here, this generalization of the logarithmic rule is not very useful. But there are two different generalizations. That's first I'm going to show you how they work, how to prove them. We're going to do a little later. And those are the generalizations of exponential and logarithmic rule. First, okay, so first, because d dx out of e to the power f of x is equal to f prime of x times e to the power f of x, right away we can notice that integral of f prime of x times e to the power f of x dx is equal e to the power f of x plus c. And look, by the same token, because derivative of ln f of x is equal to f prime of x over f of x, we can deduce that derivative f of f prime of x over f of x dx is equal to ln f of x plus c. But remember, in this case, just like in the previous situation, we either need to impose absolute value or explicitly assume that f of x is bigger than 0, which in various economic and financial implications it's rather regular.